Good afternoon, all of you, and welcome to the fifth day of the STTP Advances in Civil Engineering. Today, the speaker we have that Ms. Vaidehi Jain. She is working here since 2015. She has completed her B.Tech from Charotar Institute of Technology. She has completed her Master's in Transportation Engineering from LD College of Engineering, Ahmedabad. More than 10 research papers have been already published in national and international peer-reviewed journals. Her expertise will be in traffic engineering, road safety analysis, in airport engineering, in smart intersection designs, and she is also going to complete the few projects on the coach, which is the social innovations. She is teaching the various subjects in civil engineering apart from the transportation engineering. It's our pleasure to have you, ma'am, over here, and welcome again over here. So over to you, Vaidhi, ma'am.
Hello.
Yes.
Thank you, ma'am. Thank you, Monica, ma'am. Today I am here for presenting some advanced technologies in a transportation engineering. So let's start.
Yes, ma'am, please.
Is it visible?
Yes, ma'am, it's completely visible. You can start now.
Okay. Hello, everyone. Good afternoon. Uh, Before going much in a technology part, let's once understand what is transportation basically. So in a transportation, there are various modes. So today I'll just cover the roadway transportation because there are so many of our modes, railways, airways, waterways, pipelines, everything is covered under the transportation. So I'm not going in that part, just the roadway transportation I'll cover in this presentation and the advanced technologies used in roadway transportation or to provide the smooth roadway transportation. These are some contents which I have included in my presentation. So before going in this, like in a roadway, the very basic and the very like crucial part of a roadway is a traffic. Now we all know what is a traffic, right? Actually, we are the traffic. So well, today in today's session, we will cover that what is traffic, what are the complexes in traffic, what are the traditional methods have been used for controlling the traffic or conduction of a smooth flow of traffic, and then the technological part which can be provided and have been already provided in some other countries to for the smooth flow of a traffic. Right? These are some contents. So let's start the introductory part. Now, ITS, this is the term which has been used in a transportation world, which is intelligent transport system. Now, intelligent transport system is a heavy word, but it is not that much heavy. It is just the thing that you need to use some communication between the data and processing technologies for the smooth conduction flow on a roadway. This is just simple. The term ITS, the Intelligent Transport System, is a heavy, but it is not. So, in a early time, in something 90s or 80s, the signal introduction. Right now, we all know what is a traffic signal, but the traffic signal or the traffic signs or some pavement markings, everything is just the innovation at one time. So this is the ITS in the 90s or 80s when it has been introduced. Fine. So what is the basic use or what is the basic purpose of a innovation or the introduction of some type of a technological system in a transportation? So first one is to improve the mobility of a peoples and goods. For improvement in the mobility, for the movement, for the smooth movement of people or goods, it is very much required that with the time we need to change. Then second is increasing safety. Obviously, if you are going on a roadway, the safety is our concern. So for increasing the safety, again with the time we need to update. Then reducing the traffic congestion, very big problem in our country. The traffic congestion, we all are facing the traffic congestion in our day-to-day life. So for some kind of a reduction in that also. Then managing the incidents effectively. Whatever the incidents are happen or happening on the road, we can manage those incidents by using appropriate technology on road. And with that, by this all the purposes, by fulfilling this all purposes, we can meeting all the transport policy goals. So these are some basic purpose for the ITS implementation. The history I have already told you that uh, the signal invention is again a ITS. It was a ITS with the marking signs or pavement markings or the islands provided on the road. It is again the ITS at one time. So to understand the importance of a ITS in an early time, this is the diagram. This is the conflict diagram. Uh, this is the conflict diagram. In that, you can see in a first diagram, which is without signal control. In this first diagram, there is so much conflict over there, which is resembling with the situation. This is the real-time situation on road. In that also are you can see that the conflicts are there. Fine. So much conflict on a road. This is what the first diagram is showing. If in the time, if the signal has not been introduced, then what happened? This is the scenario. The merging, diverging, the crossing, all the types of conflicts are there. The merging conflicts means if the right movement and the straight movement are going at the time, if the signals are not there and all the movements are at the time, so some type of a flow is merging with the another type of a flow. Fine. So this is type of time of sorry, this is the merging type of a conflict in which is somewhere the in which somewhere you can face the difficulties to cross over the intersection. Fine. So to avoid that type of conflicts, we can introduce we can introduce the signal control. Now, once the signal is introduced, you can see in the second diagram with the signal control, if the first phase is open, only the straight movement and the right movement is going on. So there are much more, sorry, there are much more comfort in a traffic flow and the conflicts are reduced in this. So this is the very early invention in ITS, but it is very effective and right now we are using it. Next is, so what motivates for a intelligent transport system application? What motivates this? The negative impact of road transport. What are the negative impacts? First one is a congestion. Congestion is a very big negative impact of road transport. Because of the congestions, delays occur, then the pollution occurs. Because of the congestions, sometimes accidents also occurs. So the accident and the pollution both are the negative impacts of a road transport. Fine. In a ancient time, the traditional solution of a congestion or to reduce the pollution is adding the capacity just by improving the road infrastructure. It means the widening of a road or the expansion of a road or providing some another mode. So that was the traditional solution. But right now, it is no longer viable because we are not having that much of a space available here for the road expansion or the road widening. Fine. So that is why we need to jump in some another solution. Now we cannot use that traditional solution that by just widening or by widening of a road and your problem will be solved. So today, in our earlier days, why they are not using the technology? Because at that time they were not having that much of a broadcasting information or some broadcasting tools. Fine. But nowadays you can see the universal market is accessing the smartphones or the mobile devices. So it is much easier for travelers to reach at the correct information by using that mobile devices. Now, if you are using the ITS or the technology, then what is the function of it? We need to understand that what is the function of it. So here are the function of it. The ITS provides a flexible approach to addressing the common transportation problems, which emphasize the use of information, optimal decision making, and a high level of system adaptability. Fine. So ITS basically offers the alternatives to meeting the future travel demand. Now, what is the travel demand? The travel demand means right now there is a we have seen the congestion over there. This is again the impact of a travel demand. In earlier days, that travel demand was not that much, but right now everyone is having a vehicle. Everyone want to travel from one place to another place by their own. Plus, the public transport is still increasing, so the travel demand is increasing. So we need to find out some alternative for that to fulfilling that travel demand. Fine, that is why the ITS is here. ITS aim. What is the ITS aims? The more reliability and comfort to the individual and the more effective operation and a decision making system for the operator. Obviously, as an individual, we want the reliability and the comfort on a road. Fine. So this is the aim of ITS. And as a transportation system operators, they want the effective operations and the decision making system. The overall function of the ITS is to improve the operation of the entire system for the transport network controllers, travelers, and the other users. So in general, to fulfill this all functions, the capability of the capability of ITS should be to improve the traffic flow by reducing the congestion. Obviously, if you can reduce the traffic congestion, then the traffic flow will be automatically improved. Fine. Then the quickly detect the incident and appropriately respond to the them. It means that if any incident happen on the roadway, then in, if we can quickly detect that incident, so we can respond to that. As an example, if we are having the information that the accident happened ahead, so we can find the alternative route if we are getting that information well before the time. So this is something the example of a quickly detection of an incident. Then improve the air quality by reducing the pollution level locally and minimizing the travel delay. What it means, if the delays are there, if the travel delays are there, more decelerations are there, queuing is there, then the pollution level will be definitely increased. So if we can reduce that, if we can reduce the queuing process, or if we can reduce the delay process, then definitely we can improve the air quality. Then improve the safety by providing the advance warning before potential crash situations. We can see the signs, the warning signs at the roadsides, which is providing us the warning about the crash situations ahead. With this also, if we can introduce some technology by what we can have the information about the crash situations ahead in our vehicle or in our device, so it will be very helpful for a safety purpose. And the last one is minimize the impact of environmental, highway, and human factors that contribute to the accidents. Now, this is some basics of ITS. The basics of ITS, the fundamental requirement of ITS is data and information. If you are having data and information, you can use the ITS. The data. Now, data should be reliable. Obviously, it should be reliable. It should be up to date. It should be real time. It should be readily accessible. And it should be sufficiently comprehensive for planning and the operational purposes. Right? Um, for understanding of this, the use of it, I'm playing a video for understanding of traffic problems. Rekha. Mm.
Traffic management and quality rather than the destination. In most cases, we just want to get where we're going. Traffic is not just frustrating, but it has consequences to the environment as well. All those idling vehicles have an impact on air quality. When you're stuck and sitting behind a long line of cars, it's easy to let your mind wander over solutions to our traffic woes. But traffic management in dense urban areas is an extremely complex problem with a host of conflicting goals and challenges. One of the most fundamental of those challenges happens at an intersection, where multiple streams of traffic, including vehicles, bikes, and pedestrians, need to safely, and with any luck, efficiently cross each other's paths. Over the years, we've developed quite a few ways to manage this challenge of who gets to go and who gets to wait, from simple signs to roundabouts, but one of the most common ways we control the right-of-way at intersections is the traffic signal. I'm Grady, and this is Public Works, my video series on infrastructure and the human-made world around us. This video is sponsored by Squarespace. More on that later. There are a lot of good analogies between cities and human anatomy, and roadways are no exception. Highways are like the aorta, with a high capacity and single major destination. Small collector roads are like the capillaries, with not much capacity but a connection to every individual house and business. And in between are the aptly named arterial roadways, the medium capacity connections between urban centers. Rather than ramps, overpasses, and access roads to control the flow of traffic, arterial roads use at-grade intersections through which only a few traffic streams can pass at a time. We call this interrupted traffic flow for obvious reasons. In most cases, these intersections are the limit to the maximum throughput of the roadway. In other words, increasing the number of lanes or speed limit won't have any effect on the overall capacity of the road. The only way to increase the number of vehicles that safely travel from point A to B is to increase the efficiency of the intersection. In addition, these intersections are where a vast majority of accidents occur. For these reasons, traffic engineers put a lot of thought and analysis into the design of intersections and how to make them as safe and efficient as possible. Controlling the flow of traffic through an intersection, otherwise known as assigning right-of-way, is an enormous challenge and almost always requires a compromise of numerous conflicting considerations, including space, cost, approach speed, cycle time, sight distance, types and volumes of traffic, and human factors like habits, expectations, and reaction times. Intersections also need to be rigidly standardized so that when you come to an unfamiliar one, you already know your role in the careful and chaotic dance of vehicles and pedestrians. From a throughput standpoint, the ideal intersection would cause no interruption to flow whatsoever, but you can't put a high-five interchange on every city block. On the other hand, simple signs are cost-effective and don't require any extra space, but they can't handle a lot of volume because they create an interruption for every single vehicle passing through the intersection. You can see why traffic signals are so popular. They aren't a panacea for all traffic problems, but they do offer a very nice balance of the considerations we discussed before. Relatively low cost, minimal space requirements, and the ability to handle large volumes of traffic with only some interruption. In their simplest form, traffic signals are a set of 3 lights facing each lane of an intersection. When the light is green, that lane has the right-of-way to cross. When the light is red, they don't. The amber light warns that the signal is about to change from green to red. Beyond this basic function, traffic signals can take on innumerable complexities to accommodate all kinds of situations. Let's take a look at a typical intersection here in the US to show how they work. At each approach to an intersection, there are 3 directions vehicles can go, called movements: right, through, or left. Right and through are usually grouped together as a single movement, so a typical 4-way intersection has 8 vehicle and 4 pedestrian movements. These movements can be grouped into phases of the traffic signal. For example, the left turn movements on opposite approaches can be grouped into a single phase because they can both go at the same time without conflicts. Traffic engineers use a ring and barrier diagram to sketch out how different phases of the signal are allowed to operate. Here's the ring and barrier diagram for our example intersection. The first phase is the major street left turns. Then the major street vehicle and pedestrian through movements. A barrier to clear the intersection. The minor street left turns. The minor street vehicle and pedestrian through movements. And finally, another barrier before the cycle starts again. There are an endless variety of phasing arrangements that traffic engineers use to accommodate various intersection configurations and traffic volumes for each movement. Even the simple decision of whether to use protected or unprotected left turns takes a significant amount of analysis and consideration. Another important decision is how long each sequence of a phase should last. Ideally, a green light should last at least long enough to clear the queue that built up during the red light. This isn't always possible, especially during peak times on busy intersections. In these cases where the intersection is saturated, the green light might be extended for each phase to minimize the startup and clearance times, which are periods when the intersection isn't being utilized to its maximum capacity. The amber light needs to last long enough for a driver to perceive the warning and decelerate their vehicle to a stop at a comfortable rate. 1 second for every 10 miles per hour or 16 kilometers per hour on the speed limit is a general rule of thumb. But traffic engineers also take into account the slope of the approach and other local considerations when setting the timing for yellow lights. In most places in North America, you're allowed to enter an intersection for the full duration of a yellow light, which means there needs to be a time when all phases have a red light to allow the intersection to clear. This clearance interval is usually about a second, but can be adjusted up or down based on speed limit and intersection size. So far, we've only been talking about signals on a set timing sequence, but most traffic signals these days are more sophisticated than that. Actuated signal control is the term we use for signals that can receive input from the outside and use that information to make decisions about light timing and sequence on the fly. These types of signals rely on data from traffic detection systems. These sensors can be embedded cameras or radars, but most commonly they're inductive loop sensors embedded into the road surface. They are essentially large metal detectors which simply measure whether or not a car or truck is present, sometimes to the annoyance of bicycles, scooters, and motorcycles that may be too small to trigger the loop. Whatever the type of sensor, they all feed data into an equipment cabinet located nearby. You've probably seen hundreds of these cabinets without realizing their purpose. Inside this cabinet is a traffic signal controller, essentially a simple computer that is programmed with specific logic to determine when and how long each light will last based on the information from the detectors. Actuated control gives a traffic signal much more flexibility to handle variations in traffic load. For example, if a nearby road is closed and traffic rerouted through a signal that doesn't normally see such high demand, it may need to be reprogrammed before the closure. A light equipped with actuated control will simply see the additional traffic and adjust its phasing accordingly. Same thing with special events like concerts and sports games that create huge traffic demands on irregular schedules, and even seasonal changes in traffic like in major tourist destinations. Actuated systems can also keep you from waiting at a long light when no one's crossing in the other direction. Finally, actuated control can help by giving priority to emergency vehicles and public transportation by using specialized detectors like infrared or acoustic sensors that communicate directly with certain types of vehicles. But actuated control isn't the end of the complexity. After all, it still treats each intersection as an isolated entity, when in reality each signal is a component of a larger traffic network. And each component of the traffic network can have an impact, sometimes a major impact, on other components in the system. Take the classic example of two signals closely spaced in a row on a major roadway. If one signal gives a green but the next one doesn't, cars can back up. If they back up far enough, they can sit through multiple cycles at an intersection without being able to pass through until the light beyond clears. It's a frustrating experience for anyone. A signal is inadvertently but significantly reducing the capacity of an adjacent signal. One solution to this problem is signal coordination, where lights can not only consider the traffic waiting at their intersection, but also the status of nearby signals. This is a very common configuration on long corridors with relatively minor but frequent cross streets. The signals on the major road are timed so that a large group of vehicles, called a platoon by traffic engineers, can make it all the way through the corridor without interruption. This type of signal coordination can significantly increase the volume of traffic that can pass through intersections, but it really only works on stretches of road that don't have other sources of traffic interruptions, like driveways and businesses. If the platoon can't stick together, the benefits of coordinating signals mostly gets lost. The obvious next step in efficiency is coordination of most or all the signals within a traffic network. This is the job of adaptive signal control technologies, or ASCT. In adaptive systems, rather than individual groups of lights, all the information from detectors is fed into a centralized system that can use advanced algorithms like machine learning to optimize traffic flow throughout the city. These type of systems can dramatically reduce congestion, but they're only just starting to be implemented in major urban areas. As sensors become more ubiquitous and computing power increases, traffic management may slowly but surely be relegated from civil engineers to software developers and data scientists. On the complete opposite side of centralization, many believe that self-driving cars are the next revolution in traffic management. If every vehicle could communicate
So in the video you have seen from traditional traffic signal to some problems without traffic signal, and then the intelligent transport system application. So uh, in that video, what are the problems facing with the signals is there. So only the signal is not a option for us now. So that is why the ITS should be introduced. One more term we have heard in the video is a signal coordination. They have shown one example. If the intersections are very near, then there is a problem of stoppage at one intersection, and the another one is having a green light. So that type of a problem we all are facing in our day-to-day life. So to solve this problem, another solution is a signal coordination. This is also can be done by using some ITS applications or some detectors or the sensors. So now we'll jump into the ITS. Now, what is the technology? What is the intelligent transport system? This is the information structure of a intelligent transportation system. This is somehow very complex, but basically this is related to the traffic, then the vehicles, then the type or the classified vehicles, storage capacity of a data, and the financial institutions. These are the basic terminologies which can combinedly make a full information structure for an intelligent transport system. Fine. In it, the term traffic. So for a traffic, the first task is to manage the traffic. For the management of a traffic, again the data is required. The data related to the vehicle, the classified vehicles, the speed of a vehicle, the delay, the trips generated by the vehicle, the trips are daily trips or some guest trips are there. This type of informations are required to manage the traffic. So this is again the traffic information. Then once you are having the information regarding the traffic and the vehicle, then to manage it, the route allocation is there. Fine. Now, for the route allocation, we need to consider the commercial vehicles and the transit means the public transportations in consideration. Fine. So, if you are considering the public transport or the commercial vehicles routes over there, so in that for a management of a traffic you need to provide the another route. If the public transport is heavily on that route, so the another route should be provided. So alternative routes or the information on from the routes that which route is not heavily congested or which route is probably good for the traffic, that type of informations are required for managing the traffic. Fine. Now, once you are having the data, then the service station or the storage facility of a data is required. So, another term is a service station or the storage facility. And Then the financial institution comes in a picture, and it is playing a very crucial role in this ITS system. So this is look like a very complex, but it is not. It is a very simple to understand that just the term traffic management. For the traffic management, we require some informations regarding the vehicles, routes, trips, and the finance. Once you are having all this thing, then how the ITS will work. So this is something the working system. The working system is the traveler is there. Now the traveler wants the information. It can be regarding the traffic, it can be regarding the public transport, it can be regarding the emergency services. So the working system of ITS is the traveler will ask to the station about the information what he or she required, the traffic information if required, the traffic information, then request for the traffic information, and the service station will provide that information, that required information, to traveler by any of the mode, like a mobile device. On a mobile device you can get that information whatever you are requiring. Same way for the public transport and the emergency services, whatever the information has been asked to the service station will be got by the travelers. For an example, if you are using the maps GPS system when traveling on road, then you can get the information that how much traffic ahead, or among this route, this much of a route, which route is a shortest route, or which one is a very appropriate route for the traveler. This is the example. Again, for the public transport also, if you want that I need to book some bus or a train or something, so you can have the schedule of it, that at what time you will get the bus or a train or any public transport or the cab, and at what time you will get the availability of it, then the time will be taken by that transport system, and in how much time you will reach to your destination by using that public transport. So this is something the working system of a intelligent transport system. So by using the mobile devices you can get the information. This is the something very simple system of a intelligent transport. For that, this is the chart, or this is the flow of a working system. Now the first step is the data collection. Obviously, if you are going in any of this system, the first thing is you need to collect the data. Now, what type of a data? Data is traffic count, how much traffic is there, with the type of vehicle, the classification of vehicle, the speed of that vehicle, the location of a traffic, the travel time, the delay, the incident occurred at the place. This type of data you required for developing any of the intelligent transport system. And for collecting that data, you need some instruments or hardware like a sensors or camera, GPS. Fine. Now, this is the part data collection. Now you are having a data from any of the route. Let's select one route from one node to the another node. From first node to the second node, you are having all the data regarding the traffic volume, speed, travel time, delay, then some accidents or incidents are present over there or not, some ongoing works over there or not. Everything you are having all the real time data. Now the data transmission will comes in a picture. Data transmission. Now the rapid or a real time data what which you are having, will be transmitted from that road to the traffic management center, from road to the traffic management center, not to the traveler, because you are having a data which is in a very haphazard manner. So the traffic management center will manage those data, for then analyze those data, and after the rectification of all the errors, the cleaning of a data, after some analysis on that data, whatever the data is required by the traveler, in whatever the form it is required, it convert that haphazard data in that form, and then again the data transmission is there, and now this transmission is from traffic management center to the traveler. And this is something the intelligence system, or the intelligent information, or we can say the real time information. Again, the same example, that if you want to know that how much congestion is there at the road ahead, you are using the GPS system. In that, in the background of that system, this whole process is going on. The real time data has been collected. That data is very much haphazard. Then that data is sent it to the management center. The management center is again analyzing those data, rectifying all the errors, and providing you the real time data, that whatever you want, the congestion or the appropriate route or the time will be taken or for going on that route. This all data will be provided by the traffic management center to the traveler. Fine. So which type of real-time informations you are getting? So we have already discussed, you can get this type of real-time informations, changing in routes or diversions are there or not, some working zone is there or not, what travel speed we can get over there, if the delay will be there or not, or delay is already there or not, the travel time or accidents on road, or much more. Now, for fulfilling that, this is the ITS technology. You are having the data, transmitted the data, but for doing this, in the core part, this is the technology. These are the five components which are working on that, and finally, we are having a very managed traffic and all the informations regarding the traffic. The first one is data and information. Obviously, it is a very important, the data, the real time information regarding the traffic or the situation on road. Uh, in a data and information, these are some of the points. First one is a network supply chain. Obviously, the information supply chain is an important part of a data and sorry, data and information component. Then, for that supply chain, you obviously require the roadway sensors, the mobile reports, CCTVs, video image processing, and the user interface. These words are not that much new to us. This is a very well known words, the sensors, CCTVs, mobile, video images. These are very well known words. This is working behind the ITS technology. Then, after this data and information, you need some telecommunication ways. So, that communication ways can be wired or a wireless. Nowadays, we are using a wireless, but it can be wired communication too. Right? Now, if you are having that communication system, then two terminologies or the two another components are there. One is a vehicle control and the another one is a traffic control. Once you are having the data, information, then the communication system, then you can control the vehicle or the traffic. We'll have the knowledge about it in a next afterwards. And After this all, the very important thing is a payment technologies. This is again a part of a ITS technology. So start with the data and information. This is again one picture which is showing that what are the parts of a intelligent transport system that we have already discussed, the payment system or the communication system, network system, information management, scheduling, traveling informations. This all are the components of a intelligent transport system. So start with the data and information. Now, for the network data, which type of a data is required? First is the traffic capacity. Again, we are selecting one route. If for the one route we want to provide some ITS technology over there, so what is coming in our mind? What type of data is required? So first one is a traffic capacity. Whatever the route, whatever the section or whatever the stretch is there on which you want to provide the intelligent transport system, you have to know the capacity of existing roadway. What is the traffic capacity? Per hour, how many vehicles can pass through that stretch? It is something, the traffic capacity. Fine. So, the first and very important data is the traffic capacity. Now, the second data which should be included in this is the number of lanes. How many lanes are there? It means it is a 3-lane road or 4-lane road or divided road or a single lane road, one way. Which type of a roadway is there is again the important part or the important type of information which should be there if you are designing for any ITS technology. Then, if you are having a capacity and the lane, then what is the existing speed limit? Uh, I think you have seen, everyone have seen the speed limit signboards at the roadsides. So every stretch or the roadway is having a speed limit, pre-decided speed limit, which is the conclusion or the result of so many of analysis of a speed studies, and then the speed limit has been decided. The speeds are again of a different types. We'll not go much in that, but speeds are again of a very different types. Among the among those, we are selecting the operating speed. The operating speed is the continuous running speed of a vehicle. We are selecting that speed to decide the speed limit. Fine. Another data is availability and the type of traffic monitoring. Now, the traffic monitoring, how the traffic is right now monitored on that road is required. That data is required to implement the another traffic monitoring system or any other solution for the traffic monitoring over that stretch. And the last is a location and the description of a field devices. On that field or on that stretch, whatever the devices, either it is a roadside or on road, anything like markings are there or islands are there or signals are provided over there, anything, the roundabout is there. This type of description or the locations of a field device is necessary to have before planning the ITS technology. The network intelligence base needs to be kept current and up to date, taking into account of any significant modifications to the road networks. Means what? The data should be real time, up to date. It should not be haphazard. And real time means if any type of work is going on right now or in a future or in a recent past, everything should be included in that network data. Some permanent type of modifications are there if the new speed limits are there, or some another structures has been constructed over there. So this type of data should be included. And the temporary works, if the temporary works is going on, still we need to consider this, because the temporary work or the special events, this all are very problematic if we are going in a traffic or if we are going from that route. So once you are having a network data, sorry, once you are going, once you are having a network data, you can jump in a traffic monitoring. If data is there, you can obviously monitor the traffic. So data from the traffic monitoring has three functions. The primary three function is, first is a capacity modeling. In a previous slide, we are having a network data and that a traffic capacity is there. Fine. So the function of a monitoring is capacity modeling. How to increase the capacity, or at least whatever the capacity of that stretch or a road has been decided, at least the smooth flow with that much of a capacity. What it means, if we are selecting one stretch and the capacity of that stretch is 1,000 vehicles, let's say it is 1,000 vehicles per hour, so it is the capacity of that roadway. But actually it is not happening on that roadway. If the 1,000 vehicles are there, the smooth traffic flow is not there. So why it is not there, and how we can monitor that traffic and providing at least the decided capacity with the smooth flow on that road. This is something the traffic monitoring. Then next is a incident detection. Any of the incident is there uh, at that roadway or the stretch, we need to detect it where well before well enough time, so we can advise the road users, or by using the intelligent transport system we can provide some diversions over there or any other alternative routes over there. This is again the operation of a traffic monitoring. And the congestion monitoring, the very important is the congestion monitoring, because the congestion is the very big issue. So if the ITS or the provision of ITS cannot do this, so it is of no use. So in the traffic monitoring, the primary function, the third primary function of traffic monitoring is congestion monitoring. Right? So the basic functions will be served by information available from the variety of sources, like a systematic approach to the traffic monitoring will be needed. Uh, an organized or a planned traffic monitoring, or if the data is very organized and planned, then and then only you can use this data for the prediction of a future traffic condition. Now, if the data, whatever the data you are having, that 1,000 vehicles are there is the capacity of it, then the speed limit is something 50 kmph. But if those data are not up to date, or if those data are not very much planned, so based on those data or by using those data, you cannot uh, predict the future or a future traffic condition on that network. So the data should be very much planned and organized. It is very much important. Then by using that data, network management planning, you cannot predict the future condition of a traffic over there. Another thing is, if the data is not planned or organized, you cannot provide the route network. The data is just not used for the modifications, but the data can be used for provision of another routes or for designing the routes. fine, or for designing of a town planning or the full planning of a roadway network in a town. This type of a data are used. So if it is not organized or a plan, you cannot go much in this section also. And the last one is the national statistics on the traffic trends. Now, national statistics means in a traffic trends, you cannot decide the statistics of a traffic volume, statistics of a traffic speed, travel time delay, or the future demand of that road, or the route networking. This type of statistics cannot be developed from the haphazard data or the unorganized data. So, in a traffic monitoring, this is again a very essential part that the data should be very much organized and planned, and it should be real time. So, automatic traffic monitoring system, the intelligent transport system, which we want to apply, that will supply you the real time traffic volume, vehicle speed, the point to point journey times, and the vehicle classification. And these four data are very much useful. Fine. We need this four data with the very much accuracy and a real time. So if you can provide the intelligent transport system over there, that will be providing you this real-time data, the vehicle speed, journey time, and the classified vehicles. Right? So this data needs to be timestamped and stored with the reference to the links to which they relate together with a record of the data source. It means it should be stored with the real time of it and with the source of it, that from which source you have got this data. Fine. Now if now the second session, next session is a network information supply chain. You are having a network data. Now you understand what is the traffic monitoring. Then the supply chain, data supply chain is having this much of a parts. First step is data acquisition. Now data acquisition is what the data about status of roadway means, original roadway status, the condition of roadway, the right now traffic over there, the provisions over there, everything. The road data acquisition considers this all things, the status of that roadway. With this, the connection of one road to the another road. Fine. Whatever the stretch you have selected. If the first and second node is selected, then the second node can be connected with the another node. Fine. There is not a dead end. So the one route is connected with the another route. So we need to have the information regarding this, which is the data acquisition part. Then if you are having that data acquisition, now after that the data processing is there. Data processing is nothing but the data analysis part. Data processing is the data analysis part, and that data analysis, again, the system will bifurcate the data as per the requirement, that if it is required the vehicle types, then it is bifurcated. If the real time, it is or the travel speed or travel time delay or the future demand over the stretch, or some field status like roundabout is provided or not, or a signal is provided or not, or the proper pavement markings are there or not. This type of a data will be bifurcated in this data processing step. Fine. Then after the information management, now once the data is bifurcated, then this information should be managed according to the requirement of a traveler. So this work will be done under this step, information management, and then after the transmission and the distribution. Whatever the data required by the traveler, it should be provided to the traveler in this step, transmission and the distribution step. This is one image in which you can see that how the data is transmitted from vehicle to vehicle or vehicle to roadside unit or vehicle or inter roadside units. Means if you are going or a traveler is going from one intersection to the another intersection, at that intersection by the intelligent transport system or by the roadside units informations, it can have the information regarding, it can have the inter-vehicle communication. It means the vehicle ahead or vehicle at the back side of it, or some vehicle coming from right side or a left side from the way in traveler. This type of inter-vehicle informations can be have. Another is information to the vehicle or the traveler from a roadside. So it can be considered in a vehicle to roadside communication. Now vehicle to roadside communication, and that if any roadside or if any infrastructure is there developed over there which can be bother the traveler, so the information regarding this the traveler will have by using the technology. This is under the vehicle to the roadside communication. And inter roadside communication, inter roadside communication means at the roadside, the roadside units will have the intercommunications that what is happening at the roadside, not on the stretch, but at the roadside. If the incidents happen at the roadside, the units can pass that information from one unit to the another unit. So this is something related to the working system. For the conduction of this, we required the sensors. The sensor, the roadway sensor, is very effective and the important part for implementation of a ITS. An effective traffic surveillance and the monitoring system is a prerequisite for the ITS. Fine, and for that we need the sensors, the wide range of sensors, the different types of sensors are required for the effective implementation of ITS. Mm, So here are some sensors. The inductive loop detectors. Inductive loop detector is something, the type of a sensor which are installed beneath the pavement. By that sensor, if the vehicle is coming, uh, here is the image of a induction loop traffic sensor. The blue lines with the red markings is a sensor network which is beneath the pavement. By this, if any vehicle is coming in that sensor portion or the network, it will sense that which type of vehicle is this, what is the speed of that vehicle, weight of this vehicle, and the travel time of that vehicle from this stretch to the another stretch. This type of details can be sensed by this inductive loop sensor, and then it is provided to the roadside units or the computers or any of the devices which is connected to this. And and by use of this you can have this information. And then after this having this information, you can analyze this information. The ILD is widely used, but microwave radar detectors, microwave radar detectors are more useful than the ILD. Why is it so? The microwave radar detectors are not beneath the pavement. ILD is beneath the pavement. So if you want to reconstruct or maintain it, or some problem is there, so you have to go for the destructive method of a pavement. But in the microwave radar detector, it is not so. Microwave radar detectors are above the ground level, in fact, above the level of a vehicle's kind of at the processing. Signal processing. The microwave radar detectors are working on the waves, and by the waves coming from the vehicle that detect those radars, and by that waves it can have some informations, the regular information which is required, the vehicle, the type of vehicle, and the speed of that vehicle, everything you can get. The infrared sensors are again the widely used. In infrared sensors, there are the active and passive two types of mode. The active sensors are working on the energy coming from that energy waves coming from that vehicle, and they are using those waves. But by using that energy waves directly, you cannot get all the informations like type of that or a speed of that. So by the active infrared sensors, you are not having this uh, like particular data regarding the traffic or the vehicle. The ultrasonic detector is again the very useful, and by using that ultrasonic detector, it is kind of ILD. It is giving you the data but not so reliable. uh, Here it is the ultrasonic type of detectors. It is sensing, but not for the wide range of stretch. For the short range of a stretch, by ultrasonic type of a sensor, you can sense the vehicle, and at point information you can get. But the running information is not that much reliable by the ultrasonic type of a sensor. In the another image, you can see the pneumatic tube sensor. Now that pneumatic tube sensor is nowadays obsolete, but the very first type of a sensor which is used is kind of a pneumatic tube. The tube is installed at the stretch, and once the vehicle is going from that tube, then the tube is generating the pneumatic bubble, and then by this the control system or the connected system is getting the data of a vehicle. But this was again not that much reliable because it is not so much accurate. It is just giving you that how many wheels are passing from that, and based on that wheel axis it is counting the number of vehicles. So it is basically not giving the even the type of vehicle, not the real time speed of that vehicle. So that is why nowadays it is obsolete. Here we have already done with this induction loop traffic sensor, and the another image is there, which is the traffic signal and the sensor loop. The sensor loop is there. This is something which is not actually but implemented at a country. At the traffic signals, again the camera is there. The camera is there, and the camera is capturing the photograph if you are crossing the pedestrian line after the red light. Fine. And thus we are facing at our intersections also the cameras has been installed, and those cameras are capturing the photograph if you are not following the rules on the traffic signals. The sensor loop is sensing it. Now the ITS part is something that the sensor loop is there at the pedestrian crossing, sorry, at the pedestrian line what you can see that the red box is there. If the vehicle is coming in that red block after the red light, so the sensor loop will sensing it and give command to the camera for capturing the photograph that this vehicle has overcome the rules or has uh, or it is not following the rules. So this is something the sensing technology. Now, once the sensing technology or the sensors have captured all these things, then it is going to the device and then the mobile report is generating. Fine. So the widespread use of a cell phone can provide the useful traffic informations. Fine. Sensors are doing their job, the network is doing their job, but how the traveler will have the data or the sampling or the reports. So this is how the traveler will have the reports by the mobile applications, in that only based on one mobile sample it cannot be done. So the at least three mobile sampling should be there, and based on that triangulation system, the mobile report will work. Fine. So at least three cell phone mobile sampling is collected, and after collection of this mobile sampling, the data will verified that the information communicated from the center to the traveler is correct on in a required form. So by this, the mobile reports can be generated. To generate those mobile reports, the processing system is having this type of a components. One is a call box. Now the call box is the telephonic unit provided at the roadside with some of the intervals at the stretch in the emergency conditions, or in a not having a cell phone condition or a network and not having a network conditions. If you want, the call boxes are there. This is the one component of a mobile report generation processing system. The call box are there, in that you just need to take a receiver and dial the number which is written over there, and you will get the information about the other side. Fine. Now, if you are dialing this, if the from the call box, then how you will get this? So the service petrels should be there, and the service petrels are driven by some uh, people, some servicemen over there at the service center. They will provide you this information which is demanded by you from the call box or by the mobile phones. If the mobile phones are not there, then the call box is the option. So the service persons from the service patrols will provide informations to the call boxes or to the mobile phones or any other device by which the traveler has demanded for the information. Other than that, the crowdsourcing, other than that, service patrols to the call boxes, the crowdsourcing is something by using the social media like a Facebook or a Twitter or something, you can get the information about the route or about the stretch.
अच्छा
Like
विजय टेक्नोलॉजी फैकल्टी नहीं सर अच्छा कौन है आप
by the crowdsourcing or like on a Twitter or on a radio even, you are having the information about the road networks. Fine. We can heard on a radio that there's so much traffic area is there, the congestion is there. and this route and those route. On the Facebook, even on the Twitter, you can get this informations. And the next one, the last one, is a vehicle props. The vehicle props is something the actual vehicle is detecting the data and giving the demanded traveler by that vehicle prop. This is not much in a use, but the vehicle prop is again the processing system part. If any type of a system is not there for the working, the vehicle props are there, the original vehicles are there for original vehicles are there for this mobile report generation. Now, the next component is the CCTV cameras. We all are aware with the CCTV cameras. Like by CCTV, we can manage the we can manage all the parts of a road network management. It can be installed at the required locations for the traffic management. The traffic congestion and traffic queues can where the traffic queues or the congestion as a frequent or the increased risk is there. At that point, we can install the CCTV. The CCTV can be of two types. One is a fixed field view or another one is the wider field view. This is not requiring much discussion. The fixed field view means the giving you the all the time giving you the one field view, and the wider field view means it can cover the much more area. The next system is a video image processing system. In a video image processing system, again we are using a CCTV camera which normally have the fixed field views, but by this CCTVs, the video cameras are there, and it is not just capturing the image, but it is taking the videos of a traffic flow, and afterwards this video images is processed at the place at the service centers and then converted to the required data. So for the video image processing for the traffic detection, in that digital processing provide CCTV provides the vehicle detections. Now, once you are having all the video images, this kind of a data you will have, that the vehicle detection can be then to provide the detection over the number of lanes and the multi-zone within the lane, then it can easily modify the detection zone through the graphical interfaces. The detection accuracy is over the 96% under all the type of weather condition. This is the requirement. Now, the telecommunication part is coming. The telecommunication part. In this telecommunication, network is resembles with the nervous system of a human body. Now how it is connected, like resembling this, the telecommunication networks tie the different components of ITS together. We have learned so many of our components like data and informations, network data, supply chain, the sensors, the cameras, every parts, every data is connected together by telecommunication network. So the telecommunication is kind of this, the peoples, the roads and the vehicles which are connected to each other in all the means. Fine. So these are the four layers of that telecommunication. One is a backbone, the backhaul, the distribution and access. The overall system is the connection, sorry, to collection of a data. Then after the collection, the process on that data under the backhaul. Once the processing has been done, the distribution of those data amongst the travelers, and then the last part is the access of a data. In a telecommunication, there is a wired and the wireless both type of a communications. We all know that wired communications can be the telephonic communications, or in that the fiber optics or the Ethernet cables or copper cables can be used to provide the sensing units. And the wired communication include the wide range of technologies that vary in a performance, cost, and a bandwidth. In a wireless technology or a telecommunication, we are in nowadays we are using the wireless communications. Fine. So the wireless communication includes that a Wi-Fi or a Bluetooth or a GPS something. This type of telecommunications are the wireless telecommunications. But in that, the network is playing a very important role for the wireless telecommunication. These are some of the wireless communications, which includes in ITS the point-to-point microwaves, Wi-Fi's, the short-range communications, the Bluetooth sensor networks, and the wide area telecommunication, which is a WiMAX. Right? This is the wireless communication modes. It is not requiring much introduction. We all are using this. This is the part of ITS. Now the traffic control technology. In a traffic control technology, this type of technologies are there: the fixed time control technology, the adaptive, dynamic, and the public transport priority. Fixed time is something a signal type of control. In a signal, you are having a fixed time control. In a adaptive traffic control, the traffic can be controlled based on the requirement. If one lane is having a more traffic, then the green signal over there. If the another lane is having a less traffic, then the red time or the short period of green time over there. So this can be the adaptive type of a traffic control. The dynamic route guidance, in that if the congestion is there on a one route, the route guidance for the another route, that we can choose the alternative route for the same trip. This is something the route guidance. And the public transport priority, to co- communicate that the public transport is coming, and then we need to provide the priority to the public transport first, and then the private or the commercial transport. So these are the traffic control technologies. Under the traffic control technology, the urban traffic control is there, which is the adaptive signal control, and the public or emergency vehicle signal priority, which has been discussed earlier. Motorway control system, again it has been discussed earlier. Now the traffic control, after that the vehicle control. Traffic is the mass of a number of vehicles, but the one vehicle control, in that the very important part is the connected vehicles. The vehicles should have the connection in between. Whatever the vehicles are there on the route, all the vehicles should be connected in between. By this connection, we can maintain the safe speed and the distance in between the vehicles, and we can keep them within the lane, and avoid the unsafe overtaking. If the vehicles are connected to each other, then we can provide the safe roads and the smooth flow over the roadway. So this is something the connected vehicle theory. Under the vehicle control, in the vehicle control technology, these are again some components like onboard equipment, vehicle sensor technology, roadside equipment, or the communication network. The onboard equipment, it means in the vehicle you are having some equipment to sense or to have the information about the another vehicles. The vehicle sensor technology means the vehicle can sense the other vehicles or can sense the other roadside difficulties, everything. The roadside equipment is again, it is having the information about the roadside infrastructures, and it gives this information to the vehicles and the communication networks. Obviously the communication network is required for the connected vehicle technology. Without the communication network you cannot get the information. So the vehicle control, in that vehicle control, three parts should be there. One is a longitudinal control, another is a lateral control, and the third one, which is still the future, the self-driving vehicle or the autonomous vehicle. The longitudinal control means in the one lane, ahead or the backside vehicles are there, the condition of that and the control over that. And the lateral vehicle control means if one wants to overtake or change the lane, this is something, the lateral movement of a vehicle should be controlled for the for the provision of a safe roads and the smooth flow of a traffic. So this is something controlled by the ITS application. So the applications of the ITS applications are the one for the safety. We have already discussed so much over it that the safety, mobility, environment, and the commercial applications are there. By effective implementation of ITS, we can have the safe, the smooth, the pollution free, and the commercial and the emergency vehicles priority type of roads in our country. Now, the important part is the payment technology. If you are providing some new system or the innovative system, obviously the payment will come. So these are the mode of a payment by which you can pay about the for the technological system, the toll tax, the fare payments, the smart cards, the mobile phone payments. This all are the payment technologies which can be used for the smooth application or the effective application or the of the intelligent transport system. Now, after this all, we can identify that who will be get the benefits from the application of ITS. So the benefits of ITS can be for the road users, the public transport users, the travelers, local communities, the operators, whoever is connected with the transportation system will be benefited if we can implement the intelligent transport system effectively by by connecting all such modes which we have learned. So you will have this type of benefits: the safety, environment, pollution free environment, then the properly managed road networks, the smooth traffic flow, the security on road. This all type of benefits can be have by application of intelligent transport system. And these are some applications of intelligent transport system: the real-time parking management, the electronic toll collections, emergency vehicle notification system, automated road speed enforcement, RFID, the variable speed limits, collision avoidance system. These are some of the applications, and there are many more. And from this, some of the applications are already apply. Some of the some of the applications are already implemented in our country. So we can have the short video of that implementation.
Multi-lane, free-flow roadside systems are used for electronic toll collection on toll roads across the globe. The CAP's single gantry combines high reliability and availability with low visual impact and low needs for infrastructure, as it is installed using only one gantry, thanks to our innovative technology solutions. We have demonstrated our wide experience in electronic toll collection projects by installing and delivering equipment for about 300 toll systems with approximately 18,000 lanes in more than 40 countries, the majority in multi-lane free-flow mode. Our single gantry configuration is now installed and in operation in multiple road installations, such as the Sydney Harbour Bridge toll system in Australia and the Autopista Central toll system in Santiago de Chile. We have delivered over 100 million tags for different communication standards. The CAP single gantry supports these different communication standards, including CEN, RFID, US 915 MHz, and new VTX Wave and G5 standards. Our single gantry minimizes the visual impact to the landscape due to a modernized version of detection and classification sensors unique to the market. It manages all traffic situations, including those for heavy congestion and stop and go. The CAP single gantry performs three main processes. First, vehicle detection and classification. All vehicles passing through a gantry are automatically detected and classified to determine the toll rate. Second, reading tags installed in vehicles passing the gantry and determining which vehicles carry a tag and which don't. Third, capturing license plate and scene images. The data from these three processes are then sent to a central back-office system, where the information is used for processing and finally invoicing of customer accounts and similar. The CAP single gantry performs these three main processes and the analysis and combination of the data with highest accuracy using cutting-edge technology. Coupled with the reliability and robustness of the solution, this allows for maximum capture of toll revenue and minimum leakage. The system for vehicle detection and classification makes the exact capture of the front and rear license plates easier by using an innovative stereoscopic system with 4 cameras. It has a field of view of 30 meters, which allows to determine the precise moment of when to capture the front and rear images. Due to its convenient low height, the gantry allows the mounting of all devices on the same axis. Our 3D cameras count on a unique system, which is able to determine the vehicle direction and lane position, and when a vehicle overtakes. Our devices know exactly where every vehicle is located, identify the correct license plate associated to each vehicle, and generate the corresponding toll tariff, an indispensable functionality for highways during congestion periods. We are able to trace all vehicles accurately, no matter how they move within the field of view. We can capture the precise image of the license plate independent of the vehicle direction at the exact moment. We maintain perfect correlation between tag and vehicle. That's why vehicles with a tag and vehicles without a tag will be correctly identified and can be processed in the central back office in accordance with the business rules set by the toll road operator. Our analysis system includes a complete 3D view of what is happening on the highway. Each 3D camera provides a partial video sequence and is combined into one single view of the highway. As soon as the vehicle has been detected by our system, it will not be lost. Our modern systems process the video information and detects height, width, length and speed of each vehicle. This allows us to determine the vehicle class on highways precisely. Our toll point solution includes a reliable functionality for axle detection and axle counting. This is necessary for vehicle classification. Our solution is unique, since it does not require any equipment mounted on the road surface. CAPS Trafficom offers patented but open technology, a product with 20 years of maturity and high availability. A solution that interoperates with multiple concessions and integrated advanced and proven solutions with minimum risks and extensive experience around the world.
So in this video, we have seen the implementation of an intelligent transport system. And with this, all the connections like a service stations are there, is there. Then the network part is there, the communication part is there, the image processing part is there. Everything we have seen as in this video. So that's how we can implement the intelligent transport system. and this is the application of it. There are some real world applications are there for the daily commuters from one place to another place by using a public transport. We are also having this type of intelligent system in our country, that the public bus timings, the seat availabilities, the current location of that bus, the time taken by that particular bus to come to your destination, then the next location of that bus, this type of information regarding the public transport we are getting. This is again the application, real world application of an intelligent transport system. Another one is this is something, the nighttime public transport availability. This has been the result of some analysis that in the night time, at what points or at what nodes the people want the public transport, and then by the analysis of those data, the provision of a nighttime public transport at the places. Again, this is the application of a intelligent transport system. And the very well known thing this we are using, and we have seen this in our video too, which is the uh, RFID, the wireless system, uh, which is already implemented in our country. So these are some real world applications of a intelligent transport system. So thank you everyone for the patience and for listening me. If you have any of the questions regarding the technology, the intelligent transport system, you can ask.
Thank you so much, Vaidhi ma'am, for your enlightening lecture and the intelligent systems that could we have in our country soon, right? So the session is now open for question answers. Does anyone have any questions? Please, you may ask. Yes, Dipali ma'am, you want to ask something? Dipali ma'am, you want to ask something? You have raised your hand. That's why I'm asking you. I guess that was by mistake. So anyone else wants to ask anything?
Hello.
Yes, Dipali ma'am, do you want to ask anything?
Yeah. Actually, something was shown like that in between that if vehicle has three cell phone, some triangular, that one that I want to understand. Uh, Three cell phones are working simultaneously, then it can be detected.
Sorry, I could not hear you.
Uh, Hello, am I on
Yes,
now?
yes.
Yeah.
Yes, yes. But
So,
not clear, but audible.
yeah. Okay. Uh, Something was discussed like that in between that if a vehicle has three cell phone or a cell phone has three connection, I couldn't make it clear. Then
No,
by
no,
some
no.
triangular technology, it can be detected or something.
Okay, I'm explaining it. It is not like that. The vehicle should have a three cell phones or the connections between this. This is something that mobile report. This is under the mobile report, that based on one sampling or based on one mobile reports, we cannot conclude it. Fine. So for that, we are using, or the intelligent transport system is managing by at least the three mobile phones report. This is something what it shows, that it is not like that one vehicle should have a three mobile phones, but after all the systems, the mobile phone is the one, or any mobile device is the one who will give you the report regarding all the analysis. So that report cannot be the concluded part or the result part after just analyzing the one report. So the triangulation means we are using at least three, minimum three reports which are getting on a mobile by this intelligent transport system, and then by the verification of it, we are using those data for the travelers. This is something what it says.
Okay, thank you so much.
Okay, thank you.
Anyone wants to ask anything? I guess nobody's there for the questions. So I'm concluding for the day. You will receive your feedback link on the WhatsApp group. Please fill it on regular time, and we'll see you tomorrow for the last day of our STTP. So have a nice day and see you for the day. Bye, guys.